All right, this is video 2 for the acceleration and friction unit notes. So, getting started, Newton's second law. When we look at forces acting on an object, those forces are going to either be balanced or unbalanced. When the forces are balanced, that means the net force is zero, and the object will be in equilibrium. So that means the object will either be at rest or moving at a constant velocity. Basically, no acceleration. So equilibrium means no acceleration. However, if the net force is not zero, then the object will accelerate. And that can be found using Newton's second law, where we see that the net force equals mass times acceleration. So notice then that if the net force is the same, as the mass increases, the acceleration will decrease. So if I have the same net force acting on two objects, the least massive object will have the highest acceleration. That doesn't mean it will necessarily mean it'll be going the fastest, but it means that it will have the greatest change in velocity. So acceleration then, it means an object is going to start moving faster and faster and faster and faster, or getting slower, slower, slower. Acceleration is a change in the object's velocity. It has nothing really, it's related to velocity, but I think it's improper to say that something has a fast acceleration or a slow acceleration, because fast and slow really should go with velocity. I prefer to say something has a high or low acceleration. Now, since the net force is directly proportional to the acceleration, we can see that the acceleration will always be in the same direction as the net force. So speaking of proportionality, notice then that the way that Newton first saw this was that a net force was proportional to an acceleration. So really, what mass is a constant of proportionality. Mass is something else that we really don't understand what exactly it is, which I think is really, really interesting. All mass truly is a constant for proportionality, because the net force is proportional to the acceleration. So something to ponder and think on. Okay, now we want to be able to use this. And one of the classic ways of using this would be the Atwoods machine. Now, with this one, we have two objects that's connected by an ideal string. An ideal string does not stretch and it has no mass. It is along a massless ideal pulley. So that means that this pulley will not change either. It means that it will not affect the objects. And we got a couple of different types here. This first type, we just have two masses hanging off of a pulley, and obviously because of differences in masses, it's going to pull one object up and the other one goes down. The second type, we have one object on a flat surface. We can or cannot ignore friction. It depends. If there's wheels, I believe this is M2. If there's wheels on this one, friction is 0. If there's no wheels, then there is friction. The third type, come all the way down here, is where we have an inclined plane. I've given you a handout, or I will give you a handout for this third type. That way you can see the math involved for this one. Okay, so let's get started with the hanging masses version. So what we have is we have a pulley, one object, two object, and let's say that mass M1 is greater than mass M2. And what that means then is that object 1 is going to accelerate down and object 2 will accelerate up. And we're going to set the convention. We're going to say everything up is positive and everything down is negative, just like the Cartesian coordinate system. The first thing you have to do is create a free body diagram for each of the objects. So for object 1, we would have a tension force pulling up and a gravitational force, Fg1, pulling down. For object 2, we would have a tension force and Fg2. And what's important to realize is since this string is ideal, the tension forces in both cases are the same value because it's the same string. All right, the next thing we want to do is we want to analyze the forces. Now, this only has a y-axis, so we would take a look at the sum of forces for object 1 on the y-axis, and that would be this tension force minus Fg1, and it will accelerate, so instead of equaling 0, it's going to equal ma. And notice that object 1 is going to have a negative acceleration because it's going to go down. So rewriting this, I can say that Ft minus m1g equals negative m1a. And that's as far as I can take that equation. I have two unknowns in it, Ft and a. There's my two unknowns. All right, now let's do the same thing for object 2. And notice that m2 has a positive acceleration because it's going to travel up. So that again leaves me with an equation with two unknowns, Ft and a. And those are going to be the same for both of objects 1 and 2. They both have the same tension force, and they both are going to have the same acceleration. So if I would look at this, I want to solve this for acceleration. So what I would do is I would solve both equations for tension force. And then I would set those two equations equal to each other. And then I would just solve for a. And that gives me an expression to get the acceleration. If I wanted the tension force, I could have solved both of these equations for A, set them equal to each other, and then I could have found the tension force. All right, second type here. Let's say we have a tabletop. Here's our pulley, object 1, object 2. And looking at this, let's follow the Cartesian convention. So everything to the right is positive, left is negative, everything up is positive, down is negative. And let's say that mass m2 is large enough that it's going to accelerate object 1 in a positive direction. Okay, we're going to start the same exact way that we did the last time. And again, we want to know what the acceleration is. We got an ideal string, an ideal pulley, so all that's taken care of. So the first thing we need to do is we need to make a free body diagram. So let's talk about object 1. So for object 1, we have a normal force, we have a tension force, object 1 has some weight, and let's say that there is some kinetic friction. We won't worry about the static, let's just do the kinetic that is pulling it along. So when I analyze the forces, so when I look at the forces for object 1 on the y-axis, I have the normal force minus Fg1, and along the y-axis we have equilibrium. So we have, it should equal 0. And that tells us that the normal force then equals m1g. Then when we take a look at the sum of forces along the x-axis, well, we have our tension force minus our kinetic friction, and this time it is not in equilibrium. We're going to say that it accelerates it, so m1a. Well, that means that this Ft, now our model for friction is mu k times normal force equals m1a. And furthermore, we know that the normal force is m1g. So this leaves us with the equation Ft minus uk m1g equals m1a. And that leaves us with two unknowns, the tension force and the acceleration. So we need to take a look at object 2. For object 2, it just has forces along the y-axis. It's going to have a tension force Fg2. So in this case, the sum of forces for object 2 on the y-axis equals the tension force minus Fg2, and that's going to equal negative m2a, because again, object 2 is going to accelerate in the negative direction. So that means that this tension force minus m2g equals negative m2a. Again, our two unknowns, Ft and ma. Well, just like last time, we can solve both of these equations for the tension force. And then we can set these two equations equal to each other. All right, now just a matter of doing some algebra to find the acceleration. Gotta be careful with my algebra. And there you have it. Likewise, if I wanted to find the tension, I could have solved both equations for acceleration and set them equal to each other and done it like that. All right, that concludes the units, the notes for this entire unit.